Jan van den Brand, who is my academic sibling. We were both advised by Nandupon. Jan is now an assistant professor at Georgia Tech. He has been working a lot on dynamic data structure for metrics, like using metrics data structure to get a lot of really cool application to LP and also dynamic graph. And today you will see the application of this for multi-commodity flow and LP, I guess.
Thanks. Yeah, so this is joint work with Daniel Zhang, a PhD student at Georgia Tech. Let me start with some basic definitions. What kind of problems are we going to look at in this talk? So the first problem is, I'm going to call this single commodity flow, but really these are the typical flow problems as you know them, things like max flow or min cost flow. So you have a graph with capacities, you fix some source vertex S and target vertex T, and you want to find the largest flow that you can route in this network from S to T. So this here, for example, would be a maximum flow. And we're also going to look at something called multi-commodity flow. Let's say here we have two commodities, so this is a two-commodity flow instance. The difference is that now instead of routing one flow, we're trying to route two or more flows at the same time. So we have multiple source and sink pairs. And the important part here is that any flow that starts at this green source S must reach also the green target, right? So it's not okay if I route some flow from this green source to the blue target. That's not valid. And here we are looking, for example, for the maximum flow, like in the sum of the two flows, maximize the sum of flows from S to T. But you could also ask things like the min cost variant, where every vertex has some demand. What would be the flow in this network then that minimizes the cost if you also have costs on the edges? Okay, so this is kind of the generalization here of single commodity flow to multiple commodities. The last problem we are going to look at is, before I go to that, in this talk I want to focus on something we call the high accuracy regime. So for multi-commodity flows, there are so-called low accuracy algorithms. These scale in poly 1 over epsilon, where epsilon is like your accuracy parameter. And when we want to look at the high accuracy regime, here we want that our complexity dependence on epsilon is just logarithmic. Right? So polylog 1 over epsilon instead of just polynomial in 1 over epsilon. And we are also going to focus on the case where we allow fractional solutions, because if you try to restrict to integer solutions, the problem becomes NP-hard. And then, well, we probably can't have any efficient algorithms for that. Okay, so that's the high accuracy multi-commodity flow problem we're going to look at. The last problem I'm going to look at are linear programs. So here you have a bunch of linear constraints, and you want to minimize a linear cost function. And linear program is kind of a generalization of the two previous cases, right? You can model flow problems as linear programs. You can just say something like, for every vertex, the entire flow that goes into the vertex and out of the vertex must be 0 for every vertex except for the start and sink. And you have these constraints for both flows. And you want that the capacities are satisfied for the sum of the two flows. So we can model these previous two problems like single commodity and multi-commodity flows easily as a linear program. And yeah, that directly gives us some obvious hierarchy, right? We can say that, okay, single commodity flows, they are captured by multi-commodity flows, and they are then captured by linear programs. And this order of hardness we can also see in the algorithms. So for single commodity flow, right, min cost flow, max flow, there was recently this almost linear time algorithm. We can solve this very efficiently. The fastest algorithm that I'm going to talk about in this talk is quite a lot slower than single commodity flow, but it's still faster than if you solve a general linear program. So that would be something like m to the omega. Here omega is the matrix multiplication exponent, something like 2.38 roughly. And throughout this talk, I'm going to hide polylog complexity terms. Okay, Now, those of you who have seen things like the recent almost linear time algorithm, you probably know that, okay, these recent algorithms, they all use these continuous optimization methods together with data structures from dynamic graph area. And the same is also true for this multi-commodity flow algorithm that I'm going to talk about. And it's actually quite surprising that for multi-commodity flows, you can use graph techniques. And that's what I want to outline next. Why is it actually surprising that you could use graph techniques for multi-commodity flows? So let's look at the brief history of multi-commodity flows. So back in the 60s, it was shown that, okay, if you allow for fractional solutions, you can have a polynomial time algorithm. And later in the 80s, Kamaka came up with this central path method for solving linear programs in polynomial time. And that was very efficient. And you can just apply that linear program solver to the linear program that models k-commodity flow. And then you get some relatively fast multi-commodity flow algorithm. And since this algorithm here by Kamaka, every single improvement is just a faster linear program solver. So we have repeatedly improved linear program solvers. And since you can solve multi-commodity flow using linear programs, we also get these faster multi-commodity flow algorithms. The important part here is that, right, these are not, strictly speaking, multi-commodity flow algorithms, right? They're not graph algorithms. There's no graph technique going on. They're just linear program solvers that you apply to a certain kind of linear program. And that is super different from what happened in single commodity case, right? Spielmann and Teng showed that Laplacian systems can be efficiently solved, and that immediately implied that a whole bunch of continuous optimization algorithms became more efficient. And then it was shown also that, let's say, these continuous optimization methods, if you have a specific kind of graph problem, like the line by Adri et al. And Leo and Sitford, they have shown that the number of iterations of these continuous methods can actually be decreased if you have a flow problem. And then there were all these recent lines of work where data structures from dynamic graph area were used to reduce the time per iteration, which ultimately led to this almost linear time algorithm. So for single commodity flows, a whole bunch of graph techniques were used to get these very efficient algorithms. But somehow, none of this could be transferred to the multi-commodity case. We've developed all of these powerful tools for single commodity flow, and somehow we could not use that for these high accuracy multi-commodity flow algorithms. Yes?
You mean this running time support k, fixed k?
This is constant k, yes. I think all of these should have k 2.5, except for this one, which has k to the omega. So it's all polynomial in k, but here I'm assuming constant in yeah. Okay, so somehow it looks like multi-commodity flow is kind of different from single commodity, even though you're just adding one extra kind of flow in your graph. And that was studied, like why is that different? There was some kind of hardness results that suggest this is not just a coincidence. So back in the 70s, Ita' showed that any linear program, the task of solving that exactly can be reduced to solving a two-commodity flow instance exactly. And recently, Ding, King, and Zhang, they have extended this to this high accuracy regime where you're allowed to have some approximate solutions. What that means is that, well, every multi-commodity flow algorithm that solves it to high accuracy is a linear program solver, right? Because you can just take your linear program, transfer it into a two-commodity instance, and then use one of these algorithms. Yes?
The running time of the reduction?
What is the running time of the running time is near linear. Yeah. And also the output. So basically for every non-zero entry in the linear program, you're creating like polylog number of edges.
All right. And then, this then gives exact solutions to ZRT. And does this then give exact solutions?
Oh, so this down here does not give exact solutions because this is just for this high accuracy regime. The upper one does give exact solutions. Yeah.
And does the approximation translate or not?
Does the approximation translate? Yes, it does translate. There is two approximations here. One is kind of the optimization value that you get is only like an additive epsilon away from the optimal. And also the constraints, like we are saying something like A times X is equal to B, there is like a small error that is like an additive and epsilon times, I think it's like the Frobenius norm of the matrix or something like that. So for polynomial conditioned linear programs, everything just translates directly. Yeah. Okay. So this gives now an explanation. Why are all the multi-commodity flow algorithms linear program solvers? Well, because, well, by this reduction, they are linear program solvers. They can be used to solve linear programs. But that also kind of suggests that, yeah, maybe we can't use graph techniques to get faster algorithms. Right? Because think about it, you have a linear program. Maybe that linear program does not have any kind of graph structure. It doesn't reflect any kind of graph problem. Why would you expect graph techniques to now result in a faster algorithm if you could graph techniques to improve multi-commodity flow algorithms? There's a caveat to this idea, though, and that is these are sparse graphs that are being produced by this reduction. So that means maybe you can use graph techniques to get faster algorithms on dense graphs. And we show that this is indeed true. If you have a dense graph, we can use graph-based dynamic algorithm techniques to improve the linear program solver complexity, which is m, like the number of edges to the omega, down to root m times n omega minus 1/2. It's kind of the first improvement for multi-commodity flow here that actually does use graph techniques. And it kind of implies that, yeah, maybe multi-commodity flow was actually more graph theoretic, more combinatorial in structure than we previously thought. It's not completely equivalent to linear program solving.
And this doesn't improve general LP because the reduction increases the number of graphs.
Precisely. It does not improve general LP because, well, it's always creating a sparse graph. If the number of edges and vertices is the same, well, both the old and the new algorithm just run in n omega time. No improvement there. Yes. Okay. And that is basically the summary of the main conceptual message here, that previously all improvements for multi-commodity flow, they were just linear program solvers, improved linear program solvers. No graph techniques were being used here. And there were also hardness results that suggested that, yeah, okay, maybe you can just get improvements using faster LP techniques, faster algebraic techniques, and so on. But now we show that actually you can use graph techniques to get something more efficient, because the hardness was really just for sparse graphs. And in particular, that means multi-commodity flow in this high accuracy regime might be more combinatorial, more graph theoretic than we previously thought. Other questions so far before I go more into technical ideas? Okay. So what are the data structures? What are the graph techniques we're using here? So we are using something that's called the central path method. And you can just think of that as reduction. It says, if you want to solve some linear program, then you can reduce that to solving a sequence of linear systems. And the nice thing is that the first linear system and then the second and the third, like the sequence, it's slowly changing. So the linear systems are kind of similar, any two consecutive ones. So that's precisely where you would want to use some kind of dynamic algorithm that just maintains the solution of your linear system. And in previous work, two central data structure problems were identified. In fact, in this paper, there's basically a reduction that says if you get data structures with certain update and query complexities, you get an LP solver with certain complexities. So if you wanted to, you could just write data structure papers and get maybe faster LP solvers. One data structure problem is about matrix inversion. That's kind of algebraic. That doesn't really have anything to do with graphs. So I'm going to skip over that in this talk. What I want to focus on is something called the heavy hitter problem. So let me quickly outline what this problem is. So you're given a matrix. It's kind of a tall matrix. And what you want to do is you want to compute a matrix vector product. Now, the nice thing is we don't need to compute the entire matrix vector product. All I care about are the large entries. So you preprocess your matrix, and then you have a query operation where you get a vector h and some threshold t. All I want to know is which entries of this matrix vector product are larger than the threshold. I don't care about the small numbers, the small entries of this product. And it's slightly dynamic in that we want to have some kind of delete operation where we can remove one of these rows of matrix A. If you can solve this efficiently, then you're actually going to improve linear program solving as well. Okay. Now, there is an interesting insight here, and that is all the provable hardness for multi-commodity flows and provable hardness for linear programs in general is kind of captured by this inverse maintenance. There is currently no formal argument why this heavy hitter problem should be impossible to solve using graph techniques. And you all work here, or the majority here works on dynamic graphs. You probably multiply matrices with vectors all the time, right? We use things like the OMV conjecture to argue hardness and so on. Think of something like one step in a random walk, you have some probability distribution, the probabilities of your random walk. Like, there's tons of graph problems that can be modeled by these matrix vector products. So maybe we can actually use graph techniques here to get an efficient data structure for this matrix vector product. And we show that at least for multi-commodity flow, that is true. But I'm just conjecturing here. I wouldn't be surprised if that would also be true for general sparse linear programs, that maybe you could actually use graph techniques there because all the provable hardness is in this other data structure task. For heavy hitter, you might actually be able to use graph techniques in general. So it's kind of my open problem that I bring here for this workshop. Question, yes?
Like, why, like, do you need to do anything about the delete operation?
If you need to do anything here. So it might become more clear on the next slide why I care about the delete operation. So let's wait with this question. I go to the next slide, maybe that's going to be answered. So the question was, why do we need the delete operation here? So I said, right, this is the problem. The complexity we are hoping for is the following. So this is the precise open problem. The matrix A you're given and that you're preprocessing is a sparse matrix. You can assume something like k non-zeros per row. And we would want that the initialization is linear in the number of rows you have. And it's fine if you have some polynomial in k, some small polynomial in k. Delete operation should also be polynomial in k. And the important part is for the query operation. We want that the query operation scales in this term. This is the L2 norm of A times H squared divided by T squared. This factor here, you can think of that as like a worst case bound on how many entries in my matrix vector product are actually larger than T. So this bound tells you kind of how many entries we expect to return. But if you have a delete operation, then over time, this gets smaller, so your query operation also needs to become more efficient, needs to spend less time. Okay. If you could solve this, just black box, you plug it into like the reductions of previous work, it immediately implies that you have a sparse, tall LP solver. So any linear program that has like lots of constraints, you can solve in basically m times poly k time, and some small polynomial in n. Here n is the width, so you can think of it as once this is tall enough, this first term is going to dominate anyway. In particular, think of something like you have just polylog non-zeros per row. That would be basically a nearly linear time LP solver for these sparse linear programs. We don't know how to do this efficiently. That's the major open problem that we are left with solving. And answers to this open problem we only have for very specific special cases. If A is a very dense matrix, like it's not sparse, it's just that, let's say, every entry is non-zero, you can solve linear programs in mn time, by basically solving this heavy hitter problem specifically for dense matrices. So there's a data structure for that special case. There's also a data structure for the special case where your matrix is an incidence matrix. If it's an incidence matrix, you can also solve this efficiently. That immediately implies that any LP that uses incidence matrices like max flow, bipartite matching, and so on, they can be solved in this near linear time complexity, assuming we have at least n to the 1.5 edges. So for special cases, we know how to solve it. But in practice, most linear programs are sparse. So this is actually not all that efficient for most linear programs as they occur in practice. We want to have something that's more efficient on sparse matrices. And this is just the main open problem we have to solve. Just this one single data structure problem. Then we're done. OK. And yeah, I'm conjecturing that maybe we can use graph techniques to solve this. In the case of multi-commodity flow, we could at least prove that this is actually true. You can use graph techniques here. Questions to this open problem before I go to some proof sketch? All right. So here's an incomplete proof that doesn't work, and then we're going to fix it. Let's say this is our tall matrix A and the vector, and we want to figure out the large entries. Without loss of generality, I can assume that every non-zero entry that I have in here also occurs in again, but negated. Oh. I can just say append minus A, and my vector, I'm appending 0. It's still the same matrix vector product, right? Because I'm just multiplying zeros with this A minus. So I can just assume that every entry occurs positive and negative. That's almost the structure of an incidence matrix. Right? I can just say, OK, let's look always at the first non-zero entry in every row and the corresponding negated one, and put that into an incidence matrix. This is now a weighted incidence matrix. It's not just +1, -1. It's more like plus weight, minus weight. And I can do this for the first non-zero entry, and then again for the second non-zero entry, and so on. Assuming I have k non-zero entries, I can say the product A times H is just the sum of these incidence matrices and the vector H prime, where H prime is just the original vector with zeros appended. So instead of general matrices, I just look at incidence matrices. Yeah, question?
Yeah, I lost something. There's just one incidence matrix, or there are several?
There are k different ones.
Okay.
I'm assuming this matrix A has k non-zero entries.
Each row, each pair of non-zeros corresponding to a single
Precisely, yes. Every pair of non-zero entries in a row corresponds to like one edge in one of these matrices.
It's a sum of them.
It's a sum of them, right? It's the sum of these incidence matrices here. Yeah. So now I have incidence matrices, and I can say, all right, instead of asking, is an entry larger than T in my original product, I could just ask, is any one entry of these terms in my sum larger than T over K? If I find all these indices, then I, in particular, found all of the indices where A times H is larger. So I can restrict myself to incidence matrices, and that is really just a graph problem. What I'm saying here is, I have potentials on the vertices, and then I'm asking like which edges carry large electric flow when I'm looking at the graph that is represented by these weighted incidence matrices. So it's really just a graph problem that I'm looking at here. I can, at this point, ignore all of the algebra. This doesn't work, though. Anyone sees an issue here? You see an issue, yes?
Cancellations across the piece.
Right, we could have cancellations here. It could happen that maybe an entry here in A times H is 0 or very close to 0. I don't care about that entry. However, it could be that, let's say, B1 and B2, if I compute these products here, they're a very large positive and a very large negative value. They just happen to cancel in the sum here. So it could be that I'm returning way too many indices. And just returning one index, where I have to write that down in memory, that takes time. So it could be that this is actually too slow. So the problem is, in general, this might be too slow. You might be returning too many indices. In particular, right, we wanted that the complexity of the query operation scales in this L2 norm here of A times H. But now the complexity is actually going to scale in several smaller L2 norms. And just by like triangle inequality, that could be way larger, right? So it doesn't quite work yet. Summary here is this heavy hitter problem on sparse matrices. We could try to phrase that as a graph problem, something like given vertex potentials, which edges carry a lot of electric flow. But this, if we just do it naively, comes with a complexity blow up. The complexity of our data structure scales in the sum of these L2 norms, which could just be much larger potentially than the L2 norm of the sum, which is precisely the norm that we wanted to have our complexity scale in. So that's the problem we have. And I'm going to show that in the special case of multi-commodity flows, that can be fixed. The main question here is, can we fix that for other matrices as well? Is there a different class of sparse matrices that maybe we can now solve linear programs on more efficiently using some kind of graph technique? Okay. Other questions before I continue? No? Okay. So the special case of K-commodity flows. What we're going to look at are so-called K-commodity incidence matrices. And with a similar reduction as the one before, I'm going to reduce it to regular incidence matrices. Just as a reminder, a regular incidence matrix, right, it's a matrix where every row corresponds to an edge. And you can just say you have plus that edge weight and minus that edge weight in every row. Now, a K-commodity incidence matrix is this thing generalized, but your edge weights are not numbers anymore. The edge weights that you have are actually small K by K matrices. So I'm saying here, okay, for every edge, I have a block of K rows, and it contains a block that is some weight matrix W and a negated weight matrix W. So similar to the previous example, I have this nice property that every entry that occurs in some positive form also occurs in a negative form. So you can do the similar trick as before of splitting this into smaller incidence matrices. But now I have some extra structural guarantees onto these for these K non-zero entries. And I can use these to kind of bound these norm issues that I had previously. So what we're going to do is that we have this matrix vector problem where K consecutive rows kind of look like this here. Everything is zero except for these K by K blocks. For now, I'm just going to reorder the matrix. I'm basically reordering rows and columns as follows. This can be seen as kind of like an incidence matrix, but every entry is a K by K block. I can say, well, that's actually a K by K block where every smaller block is an incidence matrix, just by reordering rows and columns. Basically, for every edge, take the top left non-zero entry. Those are now my edges that I plug into this top left incidence matrix. I do this for every non-zero entry. So the top right entry, that corresponds now to an edge I put in the top right block. Okay. So this is just my reordering of rows and columns, and then my matrix vector product is still just a matrix vector product. The nice thing is I now have all of these small incidence matrices. Okay. Now I can, yes.
Do we have some structure in this small matrix?
In the small matrix, we have some structure. I will mention, you know what, I can actually write it down if I have a pen here.
Behind you.
Ah, thank you. Okay. The structure is roughly as follows. Let's say I have some small k-dimensional vector. Some small k-dimensional vector V. I believe it needs to be positive entry-wise. Now I look at the matrix that is the diagonal matrix with V on the diagonal. So kind of and plug V onto this diagonal. And then I'm subtracting V times V transpose divided by, I think it's the 1 norm squared. It was similar to this. I'm not 100% sure if there was a square here or if maybe there was another division by K or something like that. But this is roughly the structure. It's like a diagonal matrix minus an outer product. So it is a full rank matrix, but it kind of has this nice sparse representation. Okay. Where was I? Right. So asking, is there a large entry in A times I, is really the same as asking, okay, is there one entry that is larger than T over K, like one of these smaller products? But now I get into the same issue as before, right? If I now just run the heavy hitter problem on K-square incidence matrices, couldn't it be that I return way too many entries here compared to above here because of some cancellations of positive and negative numbers? And yeah, there is a solution here, which, let's say it this way. I tried to solve this for months. I couldn't solve it. I gave it to my student. And over the weekend, he said, it works if you just replace it by this term. Why? Here's one-page calculation that proves it works. We don't actually know why it works other than being able to verify it. Would be nice to get more intuition here, but at least I can prove that it's correct. All right. One of the special structures is that, let's see if that follows from here. I hope it does. The sum of these incidence matrices is equal to 0. So if I have this extra HL here, which is always multiplied with B, and I have a sum over J, I'm really just adding a 0 here. So this and this is equivalent. I've just added an extra 0. And it turns out that apparently these two electric flows, like the flow of B times Hj and the flow of B times HL, are similar enough that if I now look at the electric flow of these, with the difference in these potentials, that's much smaller. So I can now look at where do I have entries here that are larger than T over K. And Daniel, my co-author, has proven that, okay, the sum of these L2 norms is at most 6 times the L2 norm outside of the sum, which is like 6 times the original problem. Now note that these here add up precisely to A times H. So in a sense, if we ignore the 6 here, right, that would kind of be the Pythagorean theorem that says these flows, these vectors are kind of almost orthogonal to each other. So the main question here is, can we find for other matrices this near orthogonal decomposition into electric flows? If we could do that, we could get faster linear program solvers on that kind of matrix. So it's like a page of calculation that I'm not going to include here in this talk. It follows from, assuming I didn't make an error in defining the matrix, but it would follow from this here. So the summary here is the heavy hitter task on this more dense multi-commodity incidence matrix where you have k non-zero entries can be reduced to regular incidence matrices. And that's done by splitting this original product of A times H into k square almost orthogonal electric flows. So now we have a graph problem. We can then use graph data structures to solve this. And the question is, okay, can we get heavy hitters on more general sparse matrices? Because then we would get linear program solvers on more general kind of sparse matrices. And maybe we can even use graph techniques here. Okay. Next, I will explain how to actually solve it on incidence matrices. What are the actual graph techniques we're going to use here? Other questions so far? Yes?
What did you use from the fact that it's a multi-commodity incidence matrix?
What did I use from the fact that it's a multi-commodity flow weight matrix? If I recall correctly, the multi-commodity weight matrix looks like this, some diagonal minus these other parts. that kind of gives you, let's say, correlations between different rows. Right? If you think of this as a matrix, you kind of know there is a certain correlation between this row and the other row because.
So the diagonals are coming from the non-zero weights, right? For the barrier for Fi being non-negative, and the VIs are coming from saying that their sum is small.
Or you mean with respect to if you look at the barrier method, why is that the precise weight?
Just aligning that the V's are coming from the fact that there's some constraint gives you this diagonal.
Right. You can think of these V's as something like if you wanted to solve single commodity flow, you have these electric flows on, and you use like 1 over the slack as the resistance. These are kind of your new resistances. This guarantees that basically your flow stays positive, and this guarantees that well, you're not shooting over the capacities because there are multiple flows on the same edge.
Should that minus be a plus?
No, I think it's actually a minus, and the normalization was important to make sure that this stays PSD.
Okay. Thanks.
Right, so it might look slightly different, but roughly like this. And using that, you can then use this norm bound. You can prove this norm bound. Okay. Yeah. What are the graph techniques we use? So we said we have this heavy hitter problem. You pre-process an incidence matrix, and then we get some vector, and we want to figure out which entries are larger than T. That can be phrased as a graph problem where we say we are given a graph G with some edge weights, and then we have some query vector H, and we want to get all the edges where the difference is larger than T. Let's assume for simplicity here that all the edges have weight 1, because what you could just do is round things to nearest powers of 2 and split it into log many problems. So let's assume for now graph is unweighted. Then we are now trying to solve this problem here. Let's look at a very simple naive algorithm for this. What we could do is I just iterate over my vertices and check, is one of these endpoints larger than T over 2? If that's the case, return all the incident edges to this vertex. In this case, I'm definitely returning all the edges where the difference is larger than T, but I might be actually returning too many indices. For a similar reason as before, it could be that maybe HU and HV are both very large, but then the difference happens to be equal to 0. I would return that edge with this naive algorithm. So how can we fix this naive algorithm? And yeah, expanders are going to solve this issue for us. What we're going to do is we use the expander decomposition, where given a graph G, you can split it into small expander graphs. And for expanders, we have this Giga inequality that basically tells us for any vector that's orthogonal to the degree vector, we have this equality here. And this now allows us to bound the complexity of that naive algorithm. What we can do is, on each expander that we have, first shift H by the all ones vector so it becomes orthogonal to the degree vector. Note that I can just shift by the all ones vector without problem because I wanted to figure out which edges have large difference. I want to know where's the difference larger than T. So if I shift both these by the same amount, I'm not changing anything. So I can just shift H by the all ones vector, and then eventually, if I shift it enough, it becomes orthogonal to the degree vector. And now I do this naive algorithm where I just iterate over all the vertices, check if the value on that vertex is larger than T over 2. If that's the case, return everything incident to that vertex within that expander. Okay. So what's the complexity here? This here is about on the complexity, right? For every expander, we iterate over all the vertices and then check, okay, is HV larger than T? If that's the case, we return all the edges. Returning all the edges costs the degree of that vertex. Right? You can think of that as something that's larger than the indicator vector of you returning everything. If HV is larger than T, this fraction is larger than what? So this is a bound on the complexity here. And well, we now directly apply this G inequality, which tells us that's up to polylog factors the same as looking at the differences squared divided by T squared, which precisely is incidence matrix times the vector H over T squared. That's precisely the complexity we were hoping for. Complexity that scales in the L2 norm of the vector. So on incidence matrices, we can solve this problem efficiently using the expanded decomposition. And the expanded decomposition can be made dynamic with this pruning technique. So this deletion operation can also be supported. Okay. Right, as a reminder, this L2 norm really is just the worst case bound on how many edges would you have to return anyway. So it turns out up to a polylog factor, we're not even returning more edges than you would expect anyway, even though we're using this naive algorithm of just returning all incident edges. So to summarize, previously, multi-commodity flow algorithms, they were all linear program solvers. There were no graph techniques being used in this high accuracy regime. And it was shown that multi-commodity flows are as hard as general linear programs. So any LP can be reduced to a multi-commodity flow instance. And we show that you can actually use graph techniques. We developed this heavy hitter data structure for matrices as they occur in the multi-commodity flow problem. And open problems would be, on one hand, can you improve the algorithm further? Can you get matrix multiplication time that scales only in the number of vertices? And is it possible to improve this heavy hitter problem for more general sparse matrices? It might be possible that using graph techniques, we can actually improve something here because all the hardness proofs that we have are kind of captured with this matrix inverse maintenance part. So maybe we can use graph techniques to solve sparse heavy hitter problems. Thanks.
Question for Jan.
Does your heavy hitter need to be adaptive or just oblivious to adversary?
So if it works against oblivious adversaries, if the heavy hitter data structure works against oblivious adversaries, that's already enough in the sense that if the data structure is correct, it definitely returns all the indices that have large entry. So the whole obliviousness, the whole randomness can only mean that you're returning too many indices. But then you can just check every index. Should we return that? Does it actually cross the threshold T or not? So you can say, with high probability, after this extra filtering, your data structure coincides with some deterministically defined data structure.
Thank you.
Okay, yes.
So, I mean, you're interested in maybe more general LPs, but if, say, just 2 commodity or K commodity, is it possible to sort of like interpret this in a more simpler way, or maybe your interest is
interpreting of what's going on here?
I mean, some kind of explicitly a computation of electrical flow of one commodity and cycling through or something. I don't know if there is any possible.
So my interpretation of what's going on here, but it's not entirely accurate, would be that this augmenting flow that's computed in every iteration, we're kind of splitting that into smaller electric flows. That's at least what we're doing for this heavy hitter problem. Though it's not entirely accurate because Laplacian systems are easy to solve, but multi-commodity Laplacians, as in you have 2 multi-commodity incidence matrices and you multiply them together to get this multi-commodity Laplacian, they're as hard to solve as general linear systems. So it's unlikely that you can split this Laplacian system into, that you can split this multi-commodity Laplacian system into smaller regular Laplacian systems. So it's not entirely accurate to say that we're splitting the augmenting flow in just electric flows. It's really just for the last heavy hitter part, given some kind of vertex potentials. We're splitting that into small electric flows.
All right then. Thanks a lot, Jan. So that would conclude today.